Hello viewers and welcome to another episode of Space Science with Python. You may notice the audio quality improved a little bit today, so I hope you can follow me more easily than the last times. And you can also see on the title that we are tackling some new major topics, namely machine learning. And of course we will not dive into some neural networks today or some other fancy architectures. As always, we will start with the basics. We will set up our environment. We will get the data and so on. And then in the next sessions, we will do some engineering. We will do some data exploration and so on before we dive into a machine learning algorithm or neural network that can be used for some data scientific purpose. Of course, today, as I said, only some small introduction into something called Google Colab and also a little bit into the data. But next time I will also present you a little bit the scientific background. So yeah, just try to catch up with me a little bit, try to download the data, try to set up everything. Of course, you are free to explore the data by yourself, but I will provide the scientific insights and explanation in the next session. But what is this all about? You may notice now, based on the title and also the numbering, that this is not a single video. There will be a lot of different videos that will tackle data fetching or downloading, data engineering or feature engineering, and some other machine learning parts as well as some conclusion and also major outlook. So let's say this is our very first scientific project. And in this scientific project, we will work with something called SMASS or SMASS, the Small Main Belt Asteroid Spectroscopic Survey. So some data from some scientific publications from like 20 years ago or so, with different so-called reflectance spectra of asteroids. Now, this may sound like, okay, a little bit overwhelming, a lot of new wordings and so on. So, but don't worry, we will talk about the very basics just in a moment, but the details will follow up in the next videos. Now, before we set up our setup, let's take a look at something that is called a spectrum. So this is a spectrum of our sun. So yeah, don't be confused about the y-axis, the so-called irradiance. It's like let's say the power or the energy of the sunlight, but plotted versus the so-called wavelength of the light. So the light is particle and as well as a wavelength, is a wave. And a wave has, of course, a certain wavelength ranging from very, very small numbers to very, very large numbers. And in a certain particular range between, as you see here, around, I would say, 350 to maybe 700 or 750 nanometers, so very, very short, we have this visible spectrum. Shorter wavelengths correspond to ultraviolet and later also X-ray and gamma ray, and longer wavelengths correspond to infrared and later also to radio waves and so on. And well, the sun, of course, emits light, so this is like the spectrum of our sun. But what about asteroids? You know that, they're just like stony balls in the sky. They do not emit any light. But what are these papers all about? So let's look at my new setup here. Finally, I can do some drawing to explain you some other stuff, maybe scientific stuff. Maybe this could also be a format I will continue working on in the future. Now, first of all, let's draw our x-axis where we will draw the just give me a moment, the wavelength of the light. So here's one x-axis, here's the second one, and then we will also have here the y-axis on the left side and on the right side. So the left side here is first of all the sun. So as I said, here's the wavelength. We call it, or we write it down with lambda, and here's also lambda. And then here on the y-axis, let's do not care too much about the y-axis. It's like, let's say the power or the so-called irradiance of the emitted or reflected light. Now here we have the sun, where we are. Here's the sun, and here on the right side we have some asteroid. Now as we saw before, we have a sun with a spectrum which looks like a little bit like this, yeah, so more or less. So this is like yeah, the shorter wavelengths on the left side, like ultraviolet, and here is more the infrared light. So infrared and the UV, and especially, yeah, where the light is, let's say, yellow, so the sun emits most light, most energy. Now this thing, this light goes to some asteroid, and the asteroid, of course, reflects the light. And the light that is being reflected can, of course, be observed at the Earth. And of course, the spectrum looks totally different. It's, let's say, a little bit altered due to some reflectance, and it may look like this, for example. Yeah, so which means in this particular case, just some random case here, also, let's say UV, and here's infrared, that ultraviolet or also visible light is absorbed, so it's not really well reflected, and infrared light is reflected very well, which means that the UV light compared to infrared light is way better absorbed, or the other way around, the infrared light is reflected way better. And talking about machine learning, and you know, maybe the major topics you can tackle with machine learning, like for example classification, you may get the feeling, well, there are probably some different shapes of these so-called reflectance spectra of asteroids that correspond to different classes. And that's basically it. This is what we will tackle in the next couple of sessions. But this is all for now for the scientific background. Again, I think I will also create some YouTube videos about the science behind these spectra, or science in general. Let me know if you like this very easy format with some drawing and some iPad. So that's all I wanted to show you here with the spectrum. So what we need now is we want to do some machine learning. We need some data. We need to convert the data, and we need maybe also a platform where we can conduct our machine learning experience. Now, small spoiler, the data is not that huge. So we're not talking about giga, tera, or petabyte of data, just a few 100 or just over a little over 1,000 spectra. So really basically two-dimensional data. And but still, I would like to show you or start working not only with Jupyter Lab on our local machine, but also with something called Google Colab. So what is Google Colab? Now this is Google Drive. I meant to go here. Google Colab is something like Jupyter Lab or Jupyter Notebooks, but running in the cloud on the Google Cloud, where the code you're executing can be executed on some free servers, free runtimes to, for example, conduct machine learning experiments. So it's a free service, but there are also some other subscriptions, paid ones, for example, Google Pro or Google Pro Plus, where you have also access to more resources, or you can also close the browser and it's still running in the background, and stuff like this. I have currently the medium option. I'm currently using Google Colab Pro, as you can see on the left top corner, the CO Pro. Now this is the starting window, and we would like to fetch some data for our analysis from this SMASS, not called database, but repository. So we have here a lot of different papers with a lot of different content, and especially here down here at reference 2, we have around 1,341 asteroids from some survey with some different classifications. So we will not talk about the classifications today. We will also build an interactive spectrum plotter and so on to see what's in there, to understand the data. Today it's only setting everything up and getting the data. I would also recommend you to get some free storage or so with Google Drive. And then in my drive, just create a new folder called Colab, and there we will store all our data for this tutorial or this machine learning project, but also for other future ones. The code is also uploaded on GitHub. There will be a badge which is called Open in Colab. You can simply click on it, and then you can execute the code from today's session. So you don't have to even copy it into the Google Cloud. You can just press the button and store it in Google Cloud. But I will show you this next time when this very first session is finished. Now let's go into our Google Colab notebook now, and we are creating a new notebook. And it's loading. Just may take some time, and there we are. It looks a little bit familiar, right? We have a cell here. Looks a little bit like some kind of Jupyter notebook. We will give our file also a name. The naming will also be consistent. We will have first a number like 1, later 2, 3, and so on. So later, if you want to reconstruct the project, you just have to execute the Jupyter notebooks by the increasing number of the script. And of course, all the scripts are 100% compatible with Jupyter Lab or Jupyter Notebook. So if you don't want to use Google Colab or you want to run it locally, don't worry, the code runs perfectly locally as well. Now, to download the data I showed you, the Spectra data, we will look at the data later. We need first to import some libraries. I also prepared some code snippets already to help you a little bit and to make the tutorial a little bit faster. Just let me import some mandatory, not mandatory, some libraries that are needed for today's session. Then the very first execution may take some time. It's connecting to some runtime service, so don't be confused if this very first part may take a few seconds or so. Now we want to connect to our Google Drive. We want to store the data there, and later we would also maybe like to load our data. But in the same time, the cell should be some kind of platform agnostic. So if you run it locally, it shouldn't complain about a missing Google Colab environment or so. So let's stick with a very with a try exception clause. So first of all, we try to connect to some Google Colab instance. And if it doesn't work because we don't have the module, we will switch to some local instance. So we will try to import Google Colab and the Drive module. And we will try to mount Google Drive. So it's /G Drive. And there, let's set some kind of, I call it core path, where it's G Drive /my drive /colab, which is the folder I showed you here, my drive colab. And then we will call it, the project we will call Asteroid taxonomy, so classification or schema of the asteroids. If we do not find this module, because for example we are working locally, it will cause a module not found error, and in this case the core path will be simply blank. So we will work in the same directory as the file that we had just created, this datafetch.ipynb. Now let's execute this, and we will see that Google Colab is asking us for permission to access Google Drive files. Of course, we have to connect to it. So there was some kind of small windows opening here. I'm clicking now on my Gmail account. It asks for the permissions. You can check the information, why it's needed. You click on allow. Sometimes it also returns some API key or so, but this time here it's well integrated. It just takes some time, and then G Drive is mounted. All right. So now before we create or download any files, it's very important that what I show you is consistent with the things you are doing. So we have to be very consistent with the data. I prepared a function for this, and the function I'm using here, and I'm just doing copy paste now, and just prepared it, is a function that computes the hash value of a file. So we are downloading files, and then we are comparing it with a hash file. And this hash file, this hash value is computed with this function comp sha256. So we provide the file name in there, the hash is computed and returned, and then we can compare it with some kind of ground truth to see whether the download was successful or not. Now, before we download it, let's also have some kind of proper directory structure. And for this one, we use a pathlib path, and there we are just using the core path. Either it's G Drive or it's your local environment. And we create a new folder called data, and then I will call it level 0. So what does it mean? Of course, we are downloading raw data, unprocessed data from the internet. Later, when we process the data, we will stick with plain files. I will use something like level 1 data, level 2, level 3, and so on to indicate the, let's say, level of feature engineering or data parsing that was being performed on the data. Now, parents equals true and exists, okay, equals true. I'm switching to German. So that the folders are created, and if it's it shouldn't raise an error when we execute this command several times. Speaking of errors, mkdir. It should be exit. No, exist. Okay, not exists. Exist. Okay, now it should work. Yeah. So now we have in our Colab, we should have a new folder called Asteroid Taxonomy, and then also data level 0. So let's take a look. There we are, Asteroid Taxonomy, data level 0. So there's no data there. But you can, for example, get all the project folder, not project folder, all the project notebooks into the Asteroid Taxonomy directory, so that you have everything in one small repository. Okay, so we are done. Now we need to download 2 files. Again, I will not go into detail what these files are today. Let's take it as it is, just to be prepared for next time. So take this video also a little bit to prepare your working environment and Google Colab and G Drive before we go deeper into science and deeper into the data. Now, I have also here a small code part that I would like to copy paste. It's just a simple dictionary. The first file, the second file, the URL to some text file, and the Spectra data. So this text file here, we will take a look at this one in a moment. And this file here is a tar file that contains all the spectra of all our asteroids. So there should be like 1,400 files or so, and each file corresponds to a single asteroid, and the content of each file corresponds to a single reflectance spectrum of this particular asteroid. This bus taxonomy txt here is some auxiliary file we'll need. And the content will be described later. So we will, of course, take a look at the data. Now, we need to download the data. So let's, I would suggest to iterate through this dictionary for the, and then we are maybe splitting the URL lib.parse.url split. So files to download, the download key, and then we take the URL, and then we are generating a file name with the split. So we want to take this last part here, this tar files and this txt files, to have some pathlib naming for the files we are downloading. So pathlib path os path join. So we are joining some paths with this command again. We use the core path. Maybe it's empty in our case. In your case, if you're working locally, level 0 / and then we are using again split. So the variable we defined in line 3, and then we split it by the / and use the last entry, which should correspond to our file name. So this is then the file name. Maybe just this. And then if if the file is not available, we can then download it, or we should download it. So for example, may sound a little bit redundant or so, or stupid, but if you put all the files, the Jupyter notebooks, into your project directory, and you're downloading the files, and you want to execute, let's say, the whole pipeline, so you're creating a script where you execute all the Jupyter notebook scripts, you don't want to download the files again, right? So we check if the file is existing or not, and if it's not existing, then we are downloading it. Otherwise, yeah, this if statement will simply being skipped. So we say here files to DL URL. So just, I can just use this one here just to print the information that we are downloading something. So the first time you execute it, you will see the print command, and the second time you should probably not see it anymore. And then let's create also a download file path name. So we want to compare it with the hash value in a second. And for this, we use the URL retriever from the URL lib library. So URL lib request dot URL retrieve. There it is. The URL is, of course, what we already have in our clipboard, and then the file name equals the file name we defined earlier. And then we can compute, for example, the hash value of our taxonomy files. Yeah, so comp sh256 of the download file path name, and then we can make an assertion to see whether this hash value is correct. If not, an assertion is raised, and then your download was not successful maybe. So this appears a little bit like an overkill, but you should always do this, or at least be aware that also files can be corrupted. And if you don't check it, then, well, your machine learning algorithm, your statistics, they could differ from what's the benchmark, and then you're confused and asking yourself, well, where's the error? Where's the mistake? I did nothing wrong. Yeah, so just be aware of this. So let's download it. Yeah, classical error as always. No, I don't want to dictate. Now we downloaded the files. And since these files are tar files, we have to untar them. So that's also why I imported the package tar file in the very first cell. Now again, os path join. I use now os path join, I think now 3 times, and I will use it one more time. So feel free to create your own auxiliary function around this one. I didn't think about this, so should have done that. And then we have this smas to data target chest. Okay, I could have used also this one here, the split path split, but yeah, it doesn't matter now. And now we can extract all. And then we again have os path join. Oh, that's kind of boring. I should have created an auxiliary function. Core path. And then we are extracting the data level 0. And then tar.close. So this is our notebook. Everything runs in Colab, so quite easy. I will talk also about Colab a little bit more in the future, where you can use CPUs, you can use GPUs or also TPUs, so some kind of hardware created by Google that is optimized for TensorFlow and machine learning or deep learning in general. Now let's here extract our files first. You see here, okay, it just vanished, a small triangle that indicates where we currently are. Now let's take a look at the data, level 0, and we have some content. We have the extracted smas2 files. So there are a lot of information now here. Let's not look into the data here today. Let's take a look at this file here, at this, what was the name of it? bustaxonomy.txt. Yeah, here. And this is the file. So there's some information about that there are 1,450 asteroids. 3 columns. First the asteroid number and name. Then something called Tolen classification, and then the smas2 classification whatsoever. So the asteroids, Ceres, Pallas, Vesta, and so on, but also some others like Siegma and Merlin. I've never heard about this one. They are here on the left side, and then we have the so-called Tolen classification and smas classification. So we see here a G, C, BB, S, SK, VV, SS. So yeah, you get maybe the idea, oh, this will be a classification project probably, yeah. And of course, feel free to take the data and to do your own analysis, but I would like to do it step by step. So what we did is, as a small recap, we set up our Google Colab environment and also G Drive, where we are downloading all the files and working with them. I was talking a little bit about the reflectance spectra and what spectra are. And in the next session, we will do some feature engineering so that we will take at some point a deeper look into the spectra, into the data to understand what's going on. So my suggestion would be for next time, it will also be called Space Science with Python, but with less Python and more with science. So maybe a concept video again, maybe published somewhere next week, where I would like to talk more about these spectra, what is it all about, and yeah, why there's such a huge variety of different classes. Does it even make any sense? I hope you learned a little bit. I hope you enjoyed the video as well. I hope you enjoyed the new audio quality. I hope it's now a little bit better. I have some, I don't want to bore you with technical stuff, preamp and so on, where I'm currently adjusting the settings a little bit. But I think today should be a little bit better than the last times. Yeah. Anyway, I wish you a nice weekend, happy coding, and until next time.